Welcome to G-Fun Facts Online. Today we are standing on the edge of a mystery that is currently baffling the brightest minds in astrophysics. It is a story about a ghost that slammed into our atmosphere, a message from a desolate region of space, and a number so big it threatens to break our understanding of physics. We are talking about the Amaterasu particle. Let's transport ourselves to the high-altitude desert of Utah. It is a place chosen specifically for its silence, not just acoustic silence, but electromagnetic silence. It is dark, dry, and vast. Spanning 700 square kilometers of this scrubland is the Telescope Array project. It consists of 507 surface detectors arranged in a precise grid. They look like innocuous plastic boxes or solar stations, sitting there, waiting. They are waiting for air showers, the invisible cascades of subatomic debris that occur when a high-energy particle from deep space crashes into the molecules of Earth's upper atmosphere. On May 27, 2021, at exactly 4:35 a.m. local time, something arrived. It wasn't a meteor. It wasn't a photon from a distant star. It was a single subatomic particle, screaming through the cosmos at a speed so close to the speed of light that the difference is practically negligible. When it hit the atmosphere, it didn't just trigger one detector. It lit up 23 of them. It splashed a cascade of secondary particles across 48 square kilometers of the desert floor. This was an event of violence and power on a scale that is difficult to comprehend. When Toshihiro Fujii, an associate professor at Osaka Metropolitan University, first looked at the data during a routine inspection, he didn't believe it. His first instinct was that the equipment was broken. He thought there must be a mistake in the calibration or a glitch in the software. Why? Because the sensors were telling him that this single particle carried an energy level of 244 exa-electron volts, or EeV. He later told the press that this energy level was unprecedented in the last 3 decades. But the data was real. They named the particle Amaterasu, after the Shinto goddess of the sun in the universe. It is the second highest energy cosmic ray ever detected by the human race. To really understand why Professor Fujii was so skeptical, and why this discovery is making headlines in journals worldwide, we have to talk about energy scales. In the subatomic world, we measure energy in electron volts. A typical electron in a beam of light carries a few electron volts. Now, consider the most powerful machine humans have ever built, the Large Hadron Collider, or LHC, at CERN in Europe. This massive underground ring smashes particles together to unlock the secrets of the universe. The LHC operates at roughly 13.6 tera-electron volts. A tera-electron volt is 1 trillion electron volts. That sounds impressive, and it is. But Amaterasu operates on a different scale entirely. 1 exa-electron volt is 1 quintillion electron volts. That is a 1 followed by 18 zeros. The Amaterasu particle was millions of times more energetic than anything the Large Hadron Collider can produce. To visualize this, imagine a proton. It is infinitesimally small. Now, scale that proton up to the size of a baseball. If you threw that baseball at 95 miles per hour, the kinetic energy of that ball would be roughly equivalent to the energy of the Amaterasu particle. But here is the catch. Amaterasu wasn't a baseball. It was a single subatomic particle. It struck our atmosphere with the kinetic force of a brick dropped from waist height, all concentrated into a point smaller than an atom. It is a bullet fired by the universe. This discovery immediately brought back memories of the only other event in history that compares to it, the legendary Oh My God particle. That was detected back in October 1991, also in Utah, by the predecessor to the current telescope array. The Oh My God particle had an estimated energy of 320 EeV. At the time, physicists were stunned. It was moving so fast that if it had been racing a beam of light from the moment the Big Bang occurred, the light beam would have only beaten the particle by a fraction of a millimeter over billions of years. For 30 years, the Oh My God particle was an anomaly. It was a lonely data point. Some scientists wondered if it was a fluke, a measurement error that we just couldn't explain. But Amaterasu has changed that. Clocking in at 244 EeV, it confirms that the Oh My God particle was not a mistake. The universe really does have a mechanism, a natural particle accelerator, capable of launching matter at these macroscopic energy scales. The question that is now haunting scientists is simple. Where are they coming from? This is where the story shifts, from a story about a big number, to a story about a deep mystery. To understand why Amaterasu is so baffling, we have to look at the speed limits of the universe. We aren't just talking about the speed of light. We are talking about a distance limit known as the GZK cutoff. In 1966, physicists Greason, Zatsepin, and Kuzmin calculated a theoretical upper limit for cosmic rays. They realized that space isn't truly empty. It is filled with the cosmic microwave background, or CMB. This is the faint afterglow of radiation left over from the Big Bang. To you and me, the CMB is harmless. But if you are a proton traveling at 99.999% of the speed of light, those CMB photons appear to be high-energy gamma rays due to the Doppler effect. At energies above 50 eeV, a cosmic ray proton will collide with these CMB photons. It creates subatomic particles called pions, and this interaction drains energy from the cosmic ray. It acts like cosmic friction. The math dictates that any cosmic ray with energy above 60 eeV loses its energy very rapidly as it travels. It simply cannot survive a journey longer than about 160 to 320 million light-years. This is the GZK horizon. It means that if a particle hits Earth with 244 eeV, like Amaterasu did, it must have originated from within our local cosmic neighborhood. It couldn't have come from the distant edges of the universe because it would have burned out its energy long before it got here. So we have a constraint. We know the source must be nearby, cosmically speaking. This should make the detective work easy. We should be able to look at the arrival direction of the particle, trace the path backward, and see a massive, violent astrophysical object capable of launching it. To accelerate a particle to 244 eeV, you need a magnetic field of terrifying power. We aren't talking about standard supernovae. We are looking for active galactic nuclei, supermassive black holes at the centers of galaxies devouring matter and spitting out relativistic jets. We are looking for magnetars or gamma-ray bursts. When the science team calculated the trajectory of Amaterasu, they traced it back to a region of the sky bordering the Milky Way. They expected to see a bustling galaxy cluster, a raging quasar, or a violent star-forming region. Instead, they found nothing. The particle appeared to come from the local void. The local void is exactly what it sounds like. On a grand scale, the universe looks like a web, with galaxies clustered in filaments surrounding vast, empty bubbles. We live on the edge of the local sheet. Adjacent to us is the local void, a region of desolation stretching 150 million light-years across. It contains very few galaxies, and the ones that are there are mostly isolated, dim dwarfs. It is the last place you would look for a cosmic particle accelerator. As John Matthews, a co-spokesperson for the telescope array, put it, you trace its trajectory to its source, and there is nothing high energy enough to have produced it. That is the mystery. If the GZK limit holds true, the source must be nearby. If the source is nearby, we should see it. But the direction points to empty space. This paradox leaves physicists with a few uncomfortable possibilities, and we need to walk through them. Possibility number one is that we are misinterpreting the path. Cosmic rays are charged particles. As they travel through space, magnetic fields bend their paths. The Milky Way has a magnetic field, and there are weaker intergalactic magnetic fields. If Amaterasu was a simple proton, its energy is so high that it should have cut through these fields like a bullet through fog, bending only about 1 degree. This would allow us to point almost directly back to the source. However, if the particle was a heavier nucleus, like iron, it would have a much greater electric charge. A heavier charge means it interacts more strongly with magnetic fields. It could be bent 20 or 30 degrees. If Amaterasu was an iron nucleus, its path could have been bent so severely that it looks like it came from the local void, but actually originated from a known source, like the starburst galaxy M82 or the radio galaxy Centaurus A. But there is a problem with this theory. The composition analysis, the data on how the air shower developed in the atmosphere, suggests Amaterasu was likely a lighter particle, much closer to a proton than to iron. If it is a proton, the magnetic deflection argument falls apart. Possibility number two is that there is an invisible source. Could there be something in the local void we can't see? Perhaps there is a silent, active galactic nucleus, a black hole that fired a jet millions of years ago and has since gone dormant. The particle is just now arriving, but the gun that fired it has stopped smoking. Alternatively, some physicists have proposed topological defects in the structure of space-time itself, relics from the early universe known as cosmic strings. These are hypothetical one-dimensional cracks in the universe that could decay and release massive amounts of energy. If a cosmic string decayed in the local void, it could produce Amaterasu without an associated galaxy. Then there is possibility number three. This is the most exciting and the most terrifying option. It suggests that our understanding of particle physics is wrong. Perhaps the GZK limit is not absolute. Maybe at these extreme energies, special relativity works differently. Maybe particles interact with the cosmic microwave background in ways the standard model doesn't predict. This would be a violation of Lorentz invariance, a cornerstone of Einstein's theory of relativity. Or perhaps the particle is related to dark matter. If super-heavy dark matter decays, it could produce ultra-high energy cosmic rays. Since dark matter is everywhere, potentially clustered in voids, this could explain an origin that doesn't match visible matter. To truly appreciate the weight of this discovery, we have to respect the instrument that made it possible. The telescope array is a marvel of hybrid detection. It uses two methods simultaneously. First, the surface scintillators. These are the 507 stations on the ground. Inside each box, there are layers of material that emit a tiny flash of fluorescent light. when a charged particle passes through. They catch the footprint of the shower as it hits the Earth. Second, overlooking this grid are 3 fluorescence detector stations. These look like observatories, but instead of focusing on stars, they stare horizontally across the desert air. When a high-energy cosmic ray hits the atmosphere, it excites nitrogen molecules. As these molecules calm down, they emit faint ultraviolet light, a fast-moving, invisible streak of blue lightning across the sky. The fluorescence telescopes watch for these streaks on moonless nights. By combining the footprint on the ground with the profile in the air, scientists can calculate the energy and direction with high precision. For Amaterasu, the signal was so strong it saturated the detectors. They had to meticulously reconstruct the event to ensure it wasn't a mistake. The implications here are profound. The existence of the Amaterasu particle implies that the ultra-high energy universe is far more active than we thought. We generally believe particles are accelerated by bouncing back and forth in magnetic shockwaves, like inside a supernova remnant. To get to 244 eeV, the shockwave must be enormous and moving at relativistic speeds. If we cannot find a source in the local void, it might imply that magnetic fields in intergalactic space are much stronger than our models predict, creating a magnetic fog that scrambles the paths of these particles so badly we can't trace them. So what comes next? The discovery has accelerated calls for larger, more sensitive observatories. The telescope array is currently being expanded with the TAX-4 project to quadruple the detection area. And looking further ahead, there is the grand project Giant Radio Array for Neutrino Detection. This massive experiment proposes using 200,000 radio antennas spread over 200,000 square kilometers in China to listen for the radio pulses generated by cosmic ray air showers. We need this immense scale because particles like Amaterasu are incredibly rare. They strike any given square kilometer of Earth, perhaps once per century. Ultimately, the Amaterasu particle is a reminder of how much we still have to learn. We stand on the surface of our small planet, catching the debris of cosmic violence, trying to reconstruct the events that shaped the universe. For decades, we believed that if we just built better detectors, the sky would come into focus. We thought we would trace these energetic messengers back to the spinning hearts of black holes or the births of new galaxies. Instead, the second most powerful particle ever seen has pointed us back to nothingness. It came from the void, carrying the energy of a brick and the speed of light, and it vanished into the Utah soil. It leaves us with a question that may take another generation to answer. Until then, the detectors in the desert will keep watching, waiting for the next message from the dark. Thank you for listening to G Fun Facts Online.